Hey everyone, welcome back to Dave's Math channel. This is my first video in my sub-series on applications of first year calculus. And today I'm going to talk about one of my favorite applications, also I think one of the most important, namely Galileo's law of falling bodies. And this picture in the middle is a sort of an apocryphal illustration. The story is that Galileo proved the law of falling bodies, which basically says that falling objects fall at the same speed in the absence of wind resistance, regardless of their size. And here he is dropping two stones of different sizes off the top of the Leaning Tower of Pisa, which actually he didn't do. But he could have done this, and he would have been able to demonstrate this. Anyway, that's what the story says. But anyway, let's just begin. So let me first state Galileo's law of falling bodies. I think he came up with this. This is one of the first results he ever came up with. I think as early as 1592. I don't think anybody knows the exact year, but it was around then. It was late 16th century. Um, and there's a picture of Galileo on the right. I'm sure you guys have all seen this picture. That's what he looked like. And so, what did Galileo's law of falling bodies say? Well, basically, there's different ways to write this law. It is a law that involves calculus. That's why I've written it this way. So, equation one says that if we have this vector r, this is a vector equation, by the way. We're not going to use this form because I haven't talking about vectors. This is actually an example of vector calculus, which you usually don't learn until second year calculus when you learn multivariable calculus. But just bear with me for a few minutes. So what the law says in its most general form, it says that the second derivative of this vector r, which is has different names. Sometimes it's called the displacement. You can just think of it as position. It's really just a vector whose head points to the position of the object. You're supposed to imagine this is a very small object. Sometimes people call it a point particle or a point object. You can think of a ball, very small ball, whatever kind of object you want to think of as falling. So its position as a function of time is this vector r, and then we're taking the second derivative of that position as a function of time with respect to time. So then what the law of falling bodies says is that the second derivative of its displacement is equal to this constant which we call g, which is known as the acceleration due to gravity. So the acceleration due to gravity is another vector. It's a vector that always points downward. Actually points towards the center of the earth. But if you don't think of the earth, if you don't want to think of the earth as a sphere, which it really is, if you just want to think that you're near the surface of the earth, so the earth looks flat, and then the center of the earth is basically downward. So this is a vector whose direction is downward, and whose magnitude is approximately 9.8 meters per second squared. That's the magnitude of the acceleration due to gravity near the surface of the Earth. It does vary by a little bit, tiny amount. I think by about 1 part in 200, depending on where you're located on the surface of the Earth. So, for all essential purposes, it's a constant. And that's what the law says. But that's a little too complicated for us because we're not dealing with vectors. Like I said, we're dealing with functions of one variable. So we'd like to stick with one variable instead of three. I mean, we live in three dimensions, so displacement or position, if you like, is really a function of three variables. But we want to reduce it to a function of just one variable. So all we really care about when we're talking about the law of falling bodies is height. I mean, you can imagine just dropping a ball or throwing a ball up in the air or throwing a ball down in the air. There's really only one direction we care about, up or down. In that case, we can call the variable representing the height z. So z is just how high you are above the ground, and it's a function of time. So another way to write equation 1, which I wrote on this slide as a vector equation, you can write that as a scalar equation. You can write it as d squared z dz squared, dt squared equals minus g. Why did I put a minus sign here? Because the acceleration due to gravity is downward. I'm defining direction for z, and I'm saying that z is positive when you're going up and negative when you're going down. And in that case, since the acceleration due to gravity is downward, its magnitude, and we want its magnitude to be positive. The magnitude is g, which is 9.8 meters per second squared. We want its direction to be downward, which means that we have to put a minus sign in front. So that's what the equation says. This is now a second order differential equation in one variable. And we can solve this equation just using what we already know about calculus. So that's what I want to do now. So now we can simplify this equation a little bit more. We just noted that this quantity d squared z dt squared, if you like, z double prime of t, or the second derivative of z with respect to time, that is what we call the acceleration of the object. So another way to write this is a of t equals minus g. It just says the acceleration in the z direction of any object that's falling, free falling, if you neglect wind resistance, is equal to minus g. Pretty nice law. It says that everything near the surface of the Earth has the same acceleration, essentially. Minus 9.8 meters per second squared. It's the acceleration to Earth's gravity, which, like I said, is for all practical purposes a constant. So that's another way to write this law. But we're still not quite done. So the acceleration is easy. If anybody asks you how fast an object's accelerating that's freely falling near the surface of the Earth, you can tell them right away it's falling at 9.8 meters per second squared downward. That doesn't depend on the object, as long as there's no wind resistance, as long as you're near the surface of the Earth. But that's not a very interesting question. Another more interesting question would be, how fast is it falling? So we don't want to just know A of t, we want to know V of t. We actually want to know Z of t as well. And we can get that very easily just using calculus. So the acceleration, so the definition of velocity is the first derivative with respect to time of position or displacement, if you like. So v of t is defined as dz dt, and the acceleration is defined as the second derivative of z with respect to time, or if you like, the first derivative of velocity with respect to time. But we know what the second derivative of the displacement as a function of time is, just minus g. There should be a minus sign there. But anyway, that's the formulas we get. And now, so this is differential calculus now. But now, in order to solve for v of t or z of t, we have to do the opposite. We have to integrate using the fundamental theorem of calculus. We know that integration is the opposite of differentiation. So to get the velocity as a function of time, you just integrate the acceleration as a function of time, which we know acceleration is just minus g, which is a constant. And where our limits of integration here are some initial time, which I'm calling t naught, and then the final time is what we're calling t, and I changed the name of the variable inside the integral by calling it s now. And now, so we have the integral of minus g ds, s going from t0 to t. That's an easy integral. Minus g is just a constant. We can pull it out. And integrating dt just gives us the t minus t0. But the constant front was minus g. We can flip things around by switching the sign. We get g times t naught minus t. We can write this a little bit differently. We can just combine terms. We can say gt naught minus gt, but then gt naught has another name. That's just the initial velocity of the object. So the formula we get is v of t equals v0 minus gt. You might have seen this. I think in pre-calc, a lot of students see this formula. Because you can kind of memorize this formula. Well, you don't, but I derived it. I just derived it using calculus. Now you know where it comes from. So we're just using a little bit of calculus and Galileo's law of falling bodies. We can easily derive this formula for the velocity, the upward or downward velocity of a falling object as a function of time. Just did that. And it depends on this initial velocity, v is 0. It also depends on time, t, how long it's been falling. And the only other quantity in this equation is g, the acceleration due to gravity, which we already know that's a constant, 9.8 meters per second squared. So now we have the formula we want. Equation 5, v of t is v naught minus gt. Well, that's nice. Now we can use this formula. We can do some examples. This is where things get fun. So for the first example, let's compute the velocity of a falling object after it's been falling for 5 seconds, 5.0 seconds, and it's initially dropped from rest on top of a tall tower. I guess it has to be a tall tower in order for it to be able to fall for 5 seconds. If it was too short, it wouldn't fall that long. So anyway, let's just do this using the formula we just came up with. Well, this is pretty easy. We just apply the formula V0, in this case is 0, since we're dropping it from rest. T is 5 seconds. We just plug in the numbers, and what we get is minus 49. We get minus 49 meters per second. If you can compute the units, velocity has to be meters per second if you're doing things in metric, which it is here, and it has a minus sign because it's falling downward. So that means that its velocity, if you like, its speed is 49 meters per second after 5 seconds. That's pretty fast. I don't think you'd want to be hit by that object. And it's falling downward. So that's what you get for that example. And then example 2 is a similar example, except in this case, we're assuming that we threw the ball, or the object. It's usually easier to think of it as a ball. So imagine the object's a ball, and this time we're throwing it upward at the same speed as it landed in the last example, 49 meters per second. That's pretty fast, but I guess a good baseball player could throw that fast. Anyway, so imagine we're throwing a ball. We're throwing a ball up in the air, 49 meters per second, and we want to know what its speed is going to be after 10 seconds. And same idea, same kind of calculation. We just have different numbers to plug in. V0 in this case is plus 49 meters per second, and t is now 10 seconds instead of 5 seconds. And if you do this calculation, you'll find that you get the same answer as the last example, minus 49 meters per second. What that means is that the ball will end up falling at the same speed it did in the first example, except this case it's arriving at the same height as it did initially. We're not dropping it from the top of a tower, we're throwing it up. And by the time it comes back, it's going to have the same speed it had that we threw it up initially. And the reason it does is because, like I said, it's the same height. And halfway through the ball's journey, it reached its maximum height after 5 seconds. We didn't calculate what that height is. We could if we wanted to. We need another formula, though. A formula for height as a function of time. So that's what I'll do next. So by the same method, we got a formula for the velocity of an object in free fall after a certain amount of time. We can get another formula for the height of an object after a given time. But so we do this the same way. We use the fundamental theorem of calculus one more time. This time we integrate the velocity, since the height z of t is since v of t is the derivative of z of t with respect to t. That means by the fundamental theorem of calculus, the height z of t is the integral v of t. And we already know what v of t is. We came up with a formula for it already. So we do the same thing. This time is a little bit more complicated than the integral, because this time we're not just integrating a constant, we're integrating v0 minus gt, or I'm calling s here. And when you do that, you get v0 times t minus t0 minus 1/2 g times t minus t0 quantity squared. That's what you get when you do this integral. And you can simplify this a little bit. You don't really need t0 in here. Usually people use t0 equals 0. But you also have to have an initial height. And your initial height is what I'm calling z0 here. Remember, whenever you do an integral, there's always an integration constant you're left with. So the integration constant in this case is z0. That's the initial height of the ball. Its initial velocity is v0. That's positive if it's upward, negative if it's downward. So we have v0t, and then the last term is minus 1/2 gt squared. That's a formula. That's a nice formula. That's formula 6, and you've probably seen this before too in pre-calc. So the height of a falling object after t seconds with initial velocity, initial height z0 and initial upward velocity v0 is given by this formula. Z of t equals z0 plus v0t minus 1 half gt squared. Another very nice formula. And let's just finish up with a couple more examples. So here's an example where this is kind of like the first example. I increased the height a little bit. So imagine we're dropping an object. You probably wouldn't want to do this in real life. But imagine you were dropping an object off a tower with a height of 300 meters. That's a very tall tower. I think that's as tall as the Eiffel Tower. And like I said, you wouldn't want to do this in real life. But just imagine we're doing this. So we're dropping an object from a height of 300 meters from rest, and we want to calculate its position, its height above the ground after it's been falling for 5 seconds. Okay, well, let's do it. We just use the formula. Z of t is z0 plus v0t minus 1 half gt squared. In this case, z0 is 300 meters. That's our initial height. v0 is 0 since we're dropping the ball from rest. So second term is going to give us 0. But then the last term is minus 1 half gt squared. When you plug in the numbers, turns out you get minus 245 meters. It's actually fallen almost the whole way down after 5 seconds. It's not quite all the way down. I guess it takes about 6 seconds to fall all the way down to the ground from the top of the Eiffel Tower. Probably take a little longer because of wind resistance. And you wouldn't want to do this because the thing would be going so fast it would probably crack a hole in the ground. It's illegal to do things like this, even with a penny, I think. So anyway, but when you do this calculation, you get 55 meters for the final height. And as a final example, let's do the same problem, except this time, let's suppose that we threw it up. Instead of just dropping it from the top of the Eiffel Tower, we threw it up at 49 meters per second. Same speed we did in example 2. And then we're asked what's going to be the height of the ball after 10 seconds. Well, this shouldn't come as too much of a surprise to you guys. Remember what I said in the last example, that if you throw it up at 49 meters per second, it's going to decelerate for the first 5 seconds, reaching its maximum height, which I'm not calculating here. I think it turns out it's another 245 meters. So it'll be 545 meters above the ground after 5 seconds. And then for the last 5 seconds, it falls. Remember, it fell 245 meters first 5 seconds in the last example, example 3. Well, it's going to do the same thing here. So after 10 seconds, it's going to end up back where it started at a height of 300 meters. And after another few seconds, it's going to crack an even bigger crack in the ground. So like I said, you wouldn't want to do this. But anyway, that's how you calculate problems like this involving falling objects using Galileo's law of falling bodies. So now you know how to do that. Anyway, that concludes my video. Thank you for watching. Long live math, and I'll see you guys next time. Bye.